Hello everyone, welcome back to our live tutorial session. And in this tutorial, we're going to do the solutions to our pre-mock exams that we did. So this live tutorial is sponsored by God Academy, and please stay glued to your seat as I'm going to take you through the solutions to the problems you solved in the pre-exams mock. So I'm going to start with the first question, which says z is equal to the expression 2 plus 3i all to the power 4n plus 2 plus another expression which is 3 minus 2i to the power 4n plus 2. But the condition is saying n should be a natural number. N is a member of the natural numbers. So the problem is show clearly that z is equal to 0. So we have to prove that the expression on this right side is equal to 0. So how do we solve this problem? So now let's see. We have this whole expression 2 plus 3i to the power 4n plus 2 plus 3 minus 2i to the power 4n plus 2. Since n is a member of the natural numbers, n can't be a negative number. So the range of natural numbers n start from 1 to infinity. So positive 1 to infinity, meaning that we shouldn't expect a negative number here, neither a fraction or a rational number. So for that reason, our goal is to nullify whatever we have here. Basically, if you have an expression a plus b, for a plus b to turn 0, meaning that b should be equal to negative of a. So as I'm saying a plus b, if b is equal to negative of a, then this expression turns a minus b. Sorry, a minus a, because b is negative a. So that gives us 0. So we are going to apply the same principle here. We need to make one look like the other, but in the negative form, so that it will cancel to give us 0. So now, let me maintain the first one. I'll have 2 plus 3i to the power 4n plus 2 plus, now I'm going to express 3 minus 2i as 2 plus 3i. They should be the same before they can cancel each other to give 0. For that reason, I'm going to convert 3 minus 2i to 2 plus 3i. So I will simply do that by factorizing negative I from my expression here. So if I have expression 3 minus 2i and I factorize this negative I from my expression, you realize that here I have 2 to be positive 2 and it's a real number. So in order to remove this complex operator here attached to the 2 here, I need to factorize this complex operator out, and I have to make 2 being a positive real number. So once the negative I comes out, 2 will be positive. Then the 3 is going to give us plus 3i. So you know that I multiplying I is negative 1. Then already this I is negative, and that's going to give us positive 3i. Sorry, positive 3. If you are to multiply it back, you get this. So this is the representation of this, so that it is going to look like what you have here. So I'm writing it here, negative I, open brackets, 2 plus 3i, close brackets, all to the power 4n plus 2. So at this point, I have my expression here and my expression here being almost equal, but we have negative I here. So how do I get rid of that? So I'm going to have 2 plus 3i, 4 plus 4n plus 2 plus the negative I here. You know that I can remove that out of this power by taking it as an individual term. So 4n plus 2 multiplying 2 plus 3i, 4n plus 2. So at this point, I'm only left to get rid of this so that I'll have my two expressions being equal. So I still write 2 plus 3i to the power 4n plus 2. Once I have negative I to the power 4n plus 2, by the law of indices, you realize that I can separate this 4n plus 2 to give me negative I to the power 4n multiplying negative 1 to the power 2. Since by indices, if you have the same basis, you just add the powers, provided they are multiplying. So we can decompose this expression to give us this form. So at this point, this whole expression is multiplying 2 plus 3i to the power 4n plus 2. So we still simplify further. 4n plus 2. So if you have negative I to the power 4n, so let's take that alone and analyze. Negative I to the power 4n. I can separate this as negative 1 to the power 4n multiplying I to the power 4n. And you know that if you have a negative number to the power an even number, you surely get an even number as your outcome. So at this point, I'm going to have 1 as the outcome of negative 1 to the power 4n. You know, 1 to the power any number becomes 1 itself. And since it's a negative 1, the power is even, so it will come as a positive 1. Now for I, you realize that when you have I to the power 4, it gives 1. Why? This is because I squared is equal to negative 1. So I squared times I squared will be negative 1 by negative 1. So this also gives us 1. Expression. So let me transfer what I'm having here. So I have this. So I had this side, the negative I to the power 4n, giving me what? 1 by 1. So I had 1. So I'll replace it with 1. Now what is negative I to the power 2? If you have negative I to the power 2, you realize that the negative here will turn positive, alright, but I squared itself is going to give us negative 1. So this place turns negative 1, multiplying 2 plus 3i to the power 4n plus 2. So you have 2 plus 3i to the power 4n plus 2. 1 by negative 1 is minus the expression 2 plus 3i to the power 4n plus 2. And at this point, you can clearly see that what I have on this side is equal to what I have here. And since the operator between them is subtraction, I can clearly see that this amounts to 0. And that is the proof. So this is the end of the first problem. Let's quickly go to the second problem. So the second problem is saying that by using a substitution of W is equal to, so let me write the full question. So by using the substitution W is equal to Z squared minus Z, or otherwise find in exact form the four solutions of the equation below. So the equation is given as Z to the power 4 minus 2Z cubed plus Z minus 20 is equal to 0, where Z is a member of the complex numbers. So simply, let's go through the question. So the second question is saying, by using the substitution, W is equal to Z squared minus Z, or otherwise, meaning you can use your own substitution. But we've been given an optional substitution, which is W is equal to Z squared minus Z. Find in exact form the four solutions of the equation below. And this equation is Z to the power 4 minus 2Z cubed plus Z minus 20 is equal to 0. And Z is a complex number. So let's solve this problem. So we are substituting W is equal to Z squared minus Z. Now let's square W. So W squared will be equal to Z squared minus Z all squared. And this will give me W squared is equal to Z to the power 4. So when you are squaring this, you know Z squared minus Z. That will give us minus 2Z cubed, right? Then you have plus Z squared. So you know that W squared is given as Z to the power 4 minus 2Z cubed plus Z squared. When you come back to the equation, you realize that we have Z to the power 4 minus 2Z cubed plus Z, and we can make a substitution here by remodifying our equation given. So I have Z to the power 4 minus 2Z cubed, but I don't have the plus Z squared. So I can introduce plus Z squared, meaning you can clearly see that the coefficient of the Z squared in the main equation is 0. So it didn't appear. But we can bring plus Z squared minus Z squared, which is also 0, but will help us introduce the W squared into our equation. So we just introduce Z squared minus Z squared, which is 0, then plus Z minus 20 is equal to 0. So let's see. So at this point, I want to make my substitution here. So I'll have the Z to the power 4 minus 2Z cubed plus Z squared to be replaced as our W squared, right? So you have our W squared. So at this point, I'm going to have this side. When I want to factorize, so right now this whole section has been represented as W squared here. So we are left with this side. So let's see. Okay, so at this point, I'm to replace all the Z with W squared. So I'm left with this last expression here. And you know that W is equal to Z squared minus Z. So we have to find a way to place our W squared, sorry, our W also here. So let's see. So if I'm to factorize negative here, if I take negative Z out, sorry, negative out, I'll have Z squared here, but this is positive, right? So it will turn negative Z minus 20 is equal to 0. And you can clearly see that Z squared minus Z is what gives me W. So I'll still replace that expression. So I have our W squared minus W minus 20 is equal to 0. At this point, I have a simple quadratic equation which I have to find the values of W. So if you have W squared minus W minus 20 equals 0, you can simply punch this into your calculator and get the factors of this equation. Or we can solve it manually as we have W squared. So we realize our C, when you multiply the coefficient of A by C, negative 20, what are the factors of negative 20? That's going to give us negative 1. So we can have negative 5 then positive 4, right? So this whole expression can, so I can represent this back as, since I have negative 5 and positive 4 as my factors, I'll have w plus 5 multiplying w minus 4 is equal to 0, right? So my factors here, so let's first punch this into the calculator and see what you're going to get. So we have, so we are getting 5 and negative 4. So I just jump this side. So these factors, when I add, I'm going to get negative 1, all right. But to get your actual factors, you have to divide this by negative. So we should have got 5 and negative 4. If we had solved this, we wouldn't have made this error here. So it's not actually part of our answer. I wanted us to go through the normal way, but it's going to be a waste of time since it's the basic things you know already. So let's move straight writing the factors of W. So our W is equal to 5 or W is equal to negative 4, right? So 5 or negative 4. But you know that W is equal to, we know that W itself is equal to Z squared minus Z. So I'm going to replace my W here with what? 5. So I'll have Z squared minus Z is equal to 5. And this gives me another quadratic equation, but this time it's in complex form. At this point, in order for us to find the root of this equation, we will use completion of squares. So using the completion of squares, we always take the coefficient of what? Our b here. Then we divide it by 2. After we square, then we add it to both sides of the equation. So the coefficient of my b here, which is the negative z, is negative 1, right? So I have negative 1. And the rule says you divide this by 2, then after you square. After squaring, our final expression will be added to both sides of the equation. So I'm going to have z squared, and I'll replace this whole expression with plus negative 1 out of 2 all squared is equal to 5 plus negative 1 out of 2 all squared. I'll take my brackets out and I'll get z minus half all to the power squared is equal to 5 plus 1 out of 4, right? Because negative 1 out of 2 all squared gives 1 squared, which is 1, 2 squared, which is 4. At this point, I'm left with simplifying this further. Z minus half all squared is equal to 4 by 5 is 20 plus 21 out of 4 on the right side. I want to find z, so I need to remove this square here by taking the square root on both sides. And that will give me z minus half is equal to square root of 21 on 4. So once you have this, square root of 21 on 4 is the same as positive or negative. Yes, you have to bring that. Square root of 21, then the 4 will leave the square root as 2. So my expression z will then be equal to, I'll send the negative half on the right side, so positive half plus or minus square root of 21 over 2. I'll further simplify this as 1 out of 2 open brackets 1 plus or minus root 2 21 here. But you know this comprises two roots, so our z1 is simply half plus root of 21 over 2, and our z2 is simply equal to half minus square root of 21 over 2. So these are the first two roots, but we were asked to we are asked to find the four solutions, right? So we've done for when w is equal to 5. Let's move to when w is equal to negative 4. So we have negative 4 will be equal to z squared minus z. So let's solve that separately once again using completion of squares. So here too, I know the coefficient of my b is negative 1. I'll have z squared plus negative 1 out of 2 all squared is equal to negative 4 plus negative 1 out of 2 all squared. So this is just like what we did. All squared is equal to negative 4 plus negative half all squared is 1 out of 4. And I'll simplify this. Z minus half is equal to, all squared is equal to, negative 4 by 4 is negative 16. Then plus this one will give me negative 15 all over 4, right? Then after I take the square root on both sides, so it will cancel this squared, and I'm going to have z minus half to be equal to the square root plus or minus here negative 15 on 4. So this simplifies as z minus half on the left side plus or minus square root of negative 15 on 2. So I'm going to have z is equal to 1 out of 2 plus or minus square root of negative 15 all on 2. But I know square root of negative 15 is simply root 15i. So I'll have this to give me z is equal to 1 out of 2 in one bracket, 1 plus or minus root 15i. So you know this has two solutions, and that will be giving me my z3 and z4. So our z3 is simply equal to 1 out of 2 plus root 15i on 2. And finally z4 is equal to 1 out of 2 minus root 15i on 2. So this is the end of the second problem. Let's move to the third problem. So from the third problem, the question says, given that z is a real number, find the possible values of mu. So I have an expression z is equal to mu plus 4i all over the expression 1 plus mu I, where mu is a member of real numbers. So let's analyze this problem. So the problem is saying, given that our complex number z is a real number, when you have any complex number to be a real number, then it's a pure real number, or it's a pure, yes, it's a pure real number. Should you say real number, complex number, something like that? So realize that our complex number doesn't have an imaginary part. So we can model our z to be equal to a plus 0i, where the a is a real part. So at this point, once we know that our z is a pure real number, we only have to simplify this expression, and we will equate our imaginary part here to be 0. So let's simplify this. For division of complex numbers, you only have to find the conjugate of the denominator, then you multiply it by both numerator and denominator. So I'm going to have mu plus 4i over 1 plus mu I multiplying 1 minus mu I over 1 minus mu I. So we have to expand this. Mu by 1 is mu by negative mu I. I'm going to have negative mu squared I. Then I have 4i times 1. That is going to give me plus 4i. 4i by negative mu I. So let's take this part carefully. I by I will give us negative 1. And that will multiply the negative 1 here to make it positive. So I'll get plus 4 mu all over the expression 1 by 1, which is 1, 1 by negative mu, which is negative mu I by 1 is positive mu then mu I by negative mu I by I will give us negative 1, and it will multiply this negative to be positive. So we'll be getting plus mu. At this point, this cancels this. And at the top, I have mu plus 4, you giving me 5 mu. Then I have negative mu squared I plus 4i over the expression 1 plus mu. So at this point, what am I getting? The problem is saying that z is a pure real number, right? So let me separate what I have here into real parts. So 5 mu is a real part minus I open brackets. I'll have mu squared minus 4 for the numerator here, all over the expression 1 plus mu. So at this point, I'll have this expression as 5 mu over the expression 1 plus mu minus I multiplying mu squared minus 4 all over 1 plus mu. So I have changed the expression into the real parts and the complex parts. So I can now say that the complex part here is equal to 0, right? So I'll have, it's a pure real number, so it doesn't have an imaginary part. So z will have this expression turning into 0. So we have negative I multiplying u squared, that is mu, minus 4 all over 1 plus mu to be equal to 0. I simply cross multiply, and this gives me negative I. Mu squared minus 4 is equal to 0. My I will also go away since I'll divide through by negative I. And I'll be getting mu squared minus 4 is equal to 0. So I have mu minus 2, mu plus 2, all giving us 0. So I have my mu to be equal to 2 or negative 2. And that answers the question as we are asked to find the value of mu, the values of mu when the complex number is a pure real number. So our fourth question. So for the fourth question, it says z is equal to negative 3 plus 4i. And z multiplying W, that is ZW, is equal to negative 14 plus 2I. By showing working, find A, W in the form A plus BI. Then the B part is the modulus and argument of W. So we have been given Z to be equal to negative 3 plus 4I and ZW to be equal to negative 14 plus 2I. We've been asked to find W. So to solve this problem, you just take ZW, which is equal to negative 14 plus 2I. Then we make W the subject from this side. So I'll have W to be equal to negative 14 plus 2I over Z. And this is also equal to negative 14 plus 2I over the expression my Z is negative 3 plus 4I. So simplifying this, I'll use the conjugate. So negative 3 minus 4I over negative 3 minus 4I. These expressions, you just have to use a calculator to punch. But since I'm solving with you, let's take it systematically. So negative 14 by negative 3, we are going to get 52. Sorry, 42. So you have 42. So 42. Then negative 14 by negative 4I. So first of all, the negative multiplies the negative, it becomes positive. So we have 14 by 4. That gives 56. So plus 56I. Then I have 2I by negative 3. That is minus 6I. 2I by negative 4I. So I have I by I to be negative, and it will multiply by this negative to be positive. So I simply get plus 8. All over the expression, negative 3 by negative 3 is positive 9. Negative 3 by negative 4I is simply 12I. Then we have 4I by negative 3 is minus 12I. Then 4I by negative 4I. So I is negative, cancelling the negative to be positive 16. At this point, I have 42 plus 8, which is 50. 56I minus 6I, which is also plus 50I. All over the expression, this cancels this. 9 plus 6 is giving us 25, right? So I'm going to get 2 plus 2I as the final value for W. But once I get W, it doesn't end there. We've been simply asked to find the modulus and the argument of W. So the modulus of W, which is also the same as W bar, is giving us the square root of 2 squared plus 2 squared. And that is going to give us square root of 4 plus 4, which is 8, right? Which is the same as 2 root 2. Then let's find the argument of W. And that is giving us tan inverse of 2 out of 2. And that is equal to pi on 4. So this is simply how to solve the fourth question. Let's move to the fifth question. So the fifth question, we have an expression z is equal to open bracket 2 minus I all squared plus 7 minus 4i all over the expression 2 plus I minus 8. So the question is express z in the form x plus iy. So let's see. Express this expression here in the form x plus iy, where x and y are raw numbers. So at this point, let's take the expression 2 minus I all squared plus 7 minus 4i over 2 plus I. This expression minus 8. So to do this expression, you know that I have to take them individually. I'll take this and simplify as 4 minus 4i. Then I squared, negative I squared is simply what? Plus 1, right? So let's see. Negative I squared. I have I squared, and that is negative 1, sorry. So negative 1. So plus this expression, I'm going to use the conjugate 7 minus 4i over 2 plus I. Multiplying 2 minus I over 2 minus I minus 8. So 4 minus 4i minus 1 plus, within these brackets, 7 by 2 is 14. 7 by negative I is minus 7i. Negative 4i by 2 is negative 8i. Negative 4i by this, I'll have I by I to be negative 1. Then it will multiply by this negative to be positive. But still, this is still negative. So I have minus 8 all over the expression. This is just difference of 2 squared. So you have 4 plus 1. But let's simplify. 2 by 2 is 4. 2 by negative I is minus 2i. 2 by I is plus 2i. I by negative I is plus 1. Minus 8. So I still have 4. So 4 minus 4i minus 1 plus the expression 14 minus 8 is giving me 6, right? Then negative 7i minus this will give me negative 15i over the expression. This cancels this over 5 minus 8. So let's see what you're going to do here. So I have 4 minus 4i minus 1 plus. So what is this? 14. So what is this expression here? You are going to have 6 over this to be 1.2 minus 3i then minus 8. So let me enter what I have here. So let's check one thing here. Negative 4i by negative I. So let's see this expression here. So if you have negative 4i by I, you are going to simply get what? Positive 4i. Positive 4i squared, yes. So that is giving us minus 8. So that is it. So 4 minus 4i minus 1 plus 1.2 minus 3i minus 8. At this point, I'll just add my row part. 4 negative 1 will give me 3 minus 4i. 4. So I'll have 4i here plus 1.2 minus 3i minus 8. So 3 minus 8 will give me negative 5. Negative 4i plus 3 minus 3i will give me negative 7i. And I still have a 1.2 here. So when I add it to it, I'll be getting negative 5 plus 1.2. That is negative 3.8 minus 7i. Please let's check these parts before we proceed. So there is a mistake here. So from this part, I was multiplying 4i by negative I. So it should have given me minus 4, not 8. Sorry. So this place is minus 4. So 14 minus 4 should give me 10. So here will give me 2. So I'll have this part being 2. Then this part was 4. So this is 4. So now I simply get plus 2. So 3 minus 4i plus so it's 2 minus 3i minus 8. Then at this point, I will get 3 plus 2, which is 5. So let me get 5 minus 7i minus 8. So 3 plus 2 is 5 minus 8 is negative 3. Negative 4i minus 3i is negative 7i. And this is our simplification. This is our simplification. So it will get x to be equal to negative 3, then y to be equal to negative 7 after our simplification. So let's move to our sixth question. So question 6, we have z squared is equal to 21 minus 20i. And the problem is we should solve this equation. So we have different ways of solving this equation. But let's take this part. Let our complex number be equal to x plus iy. Therefore, you have x plus iy all squared to be equal to 21 minus 20i all squared, right? So this gives me, sorry, this part will not be squared. Actually, is z squared equals this? So z squared, so z is the only thing to be squared here. So it's equal to 21 minus 20i. So at this point, I'll square this and I'm going to get s squared minus 2xyi. Then I'll square this side and that is going to give me minus y squared is equal to 21 minus 20i. So I'll group this into real parts, then imaginary parts. So at this point, s squared minus y squared will be equal to the real part 21. Then negative 2xyi should give us negative 20i. Solving these equations, we are going to get the value for our equation here. So see, at this point, I can tackle the second. So this is first equation, equation 1, equation 2, right? I'll divide through by negative 2i, and that is going to give me xy to be equal to, that is 10. This is our third equation. So from here, I can say that s is equal to 10 on y. Then I'll just bring it back to my first equation here. So I'll have 10 on y all squared minus y squared is equal to 21. This is going to give me 100 over y squared minus y squared equals 21. So I'll simply have 100 minus y to the power 4 is equal to 21 y squared. So grouping all this together, I'll have y to the power 4, moving this side to that, plus 21 y squared minus 100 is equal to 0. So I'm to solve for the values of y, and at this point, since we are in y to the power 4, I can express y squared all squared plus 21 y squared minus 100 is equal to 0. So I'll make y squared be a letter, let's say a. I'll have a squared plus 21a minus 100 is equal to 0. So at this point, what are the values of a? We can put this into the calculator to get the values of a. So a is equal to, so a is either, so let's see something here. I have a to be equal to either 4 or negative 25. So once I get the values of a to be a, which is 4, negative 25, I know that my y squared was represented as a. So this y squared, I replaced it with a, and I had a squared. This y squared was also replaced as a. So to get the actual values of y, I will simply solve for what? Y squared from a. So to get y is simply equal to square root of what? A. And at this point, I'll have a, which is what? 4. So y is equal to square root of what? 4. And that is going to give me plus or minus 2. But now let's see. Our a is what? Negative 25 for the second part. We can't have square root of negative 25, so we will not consider that one. We are looking out for the values of what? So let's see the question back again. See, we are solving for this equation. Solving for this equation, we need two roots of the equation. And to get the two roots of the equation, we are supposed to get two values for both x and both y. But here we would have gotten 4 values for each. But since this is negative 25, we will not consider this. Though we are in complex numbers, but when this here is not complex numbers, we were making some substitutions and we are applying polynomials here. So this, we don't consider the complex numbers system here because this is not part of our solution. It's the method we use. That is why we had this system. So let's see. I'll have my y to be equal to either positive 2 or negative 2. Then I have to find the corresponding x. I have from the beginning here that x is equal to 10 on y. So if s is equal to 10 on y, then I'll have x to be equal to, when y is 2, I'll get x to be 5. And when y is negative 2, I'll get x to be equal to negative 5. Therefore, you can clearly see that we have 5 plus 2i. Then the next root is what? Negative 5 minus 2i to be the root for the equation given above. And this is the solution for the 6th question. So let's see the 7th question. So for question 7, I'm having find the square roots of 1 plus square root of 3i. So you have to find the square root of this complex number. Whenever you are given this type of questions, we have different ways of doing that. But you have to take the approach that will be very simpler and friendly to you. So you can represent this complex number here as z is equal to 1 plus I square root of 3. So at this point, the question is saying we should find the square root of this. So I'm going to represent, so this is the square root as the question is demanded. So this is the same as what? Z squared is equal to 1 plus I root 3. So at this point, we can do it exactly as we did the previous question. So I'll have z to be equal to a plus bi. Then I can make a plus bi all squared to be equal to 1 plus I root 3. So you can clearly see that you have different ways of putting up the question. So here is find the square root of this. But the other one, we were solving an equation like this. So depending on how the question will be put, the approach may be the same. So at this point, we just multiply what I have here, a squared plus 2abi. Then I'll have minus b squared is equal to 1 plus I root 3. So I'll have my a squared minus b squared to be equal to 1, 2abi to be equal to square root of 3i. Then we can make this equation 1, this equation 2. So at this point, I can divide through by my I and I'll have 2ab to be equal to root 3. So I'll make a the subject and I'll have a to be equal to square root of 3 over 2b. And I'll have to put it here. So square root of 3 over 2b all squared minus the b squared is equal to 1. So this gives me 3 on 4b squared minus b squared is equal to 1. Then I multiply through by my 4b squared and I'll get 3 is equal to minus 4b to the power 4 is equal to 4b squared. So this is giving me 4b to the power 4 plus 4b squared minus 3 is equal to 0. So this is exactly like the question we just solved. And at this point, I'll make my b squared, let's say z. So I'll have 4z squared. So let me write it. B squared is equal to z. So 4z squared, right, plus 4z minus 3 is equal to 0. Now, let's find the values of z from this equation. So 4, negative 3, you get z to be equal to half, then z is equal to negative 3 on 2. So at this point, I'll make, you know that b squared is equal to z. I'm looking for the values for b. So I'll have b squared is equal to 1 out of 2. So b is going to be plus or minus what? Square root of half. B squared is also equal to negative 3 out of 2. And as I explained earlier, I said whenever you are using normal quadratic method to solve your complex numbers, when you get this, you shouldn't solve because it doesn't exist. You can't have any number squared to be a negative number, right? So you just tackle this. So you are going to have b1 to be equal to negative of this value, negative 1 on root 2. Then b2 to be equal to the positive version, which is 1 out of root 2. Now, using b, I can find my corresponding a. Since my a is simply square root of 3 over 2b. So I can find the corresponding values of a, and I'll get a is equal to square root of 3 all over 2 multiplying the expression root of 1 out of 2, like this. So here, I'll have a is equal to, I'll take root 3 out of 2 out. Then this expression here. So I can make it this way. I can make it half out. Then elements in the square root will be 3 over half. And this will be equal to 1 out of 2. This becomes what? 6, root 6. Now I'll have a to be equal to square root of 3, 2 multiplying the b. But the b is giving us negative of what I had. So negative square root of half. So without solving, I can say that my a2 will be equal to negative half square root of 6. Therefore, my solution is a plus bi. So my a, I'll take the positive side, that is half root 6 plus half under the square root like this. Then my a2 will simply be equal to negative half root 6 minus root of half, and that gives us the values for the square root of what the expression 1 plus I root 3. Now let's solve for our 8th question. So we have simplify 2 plus 3i to the power 1 minus I. So this problem here is an application of logarithm of complex numbers. So whenever you are being given logarithm of complex numbers, you make our complex number be equal to an unknown z, right? So 2 plus 3i to the power 1 minus I. At this point, you take ln on both sides. Ln z is equal to ln 2 plus 3i to the power 1 minus I. So ln z will be equal to 1 minus I multiplying the natural log of 2 plus 3i. So at this point, ln z is equal to simplify, I have to convert this to the polar form. So 2 plus 3i to the polar form, I'll have my r to be equal to square root of 2 squared plus 3 squared. This is giving me square root of 4 plus 9, that is root 13, right? While the argument is tan inverse of 3 on 2. So what is tan inverse of 3 on 2? So that's giving me 56.3. So 31. So I can divide this by 180 to get a corresponding angle in pi radians. So this is the same as 0.313 pi. So once I have this, I'll replace what I have within the argument of the natural log with this expression. So I have 1 minus I multiplying the expression natural log of r, which is root of 13, multiplying e to the power I, open brackets, my theta is 0.313 pi. Then I'll use the extended argument as 2 pi k, right? So once I have this expression, ln z here will be equal to, by logarithm, this whole thing here. But first of all, let me divide it. So I have root 13 multiplying this. So logarithm rule say that you have to split it. So the expression ln 13, root of 13, sorry, then plus natural log of e to the power I multiplying 0.313 pi plus 2 pi k. So at this point, I'll have 1 minus I ln 13, sorry, ln root of 13. Natural log of root of 13 is giving us 1.282 plus this expression. I'll have the whole exponent coming down, and I'll have I 0.313 pi plus 2 pi k. So ln E is 1, so ln E vanishes. So this expression will now be simplified as ln Z to be equal to 1 minus I. 1 minus I so 1 minus I, then multiplying the expression 1 plus 1.282 plus, here I'll multiply through. So at this point I'll have let me find the principal argument of this. So let me find when k is equal to 0 to solve this. So when k is equal to 0, I'll have I 0.313 pi. So here ln Z will be equal to, I'll do this multiplication. 1 by this, I'll get 1.282 plus I 0.3135 minus 1.282, then minus this will give me plus 0.313 pi. So at this point I'll have 1.282 minus this, and that will cancel out here. Sorry, at this point I should have introduced the I, so it can cancel. So let me remove my cancellation. So here I'll have I here, then I'll have ln Z is equal to 1.2. So I'll have 1.282 plus 0.318 pi. So we can multiply this by putting in the value for pi, 3.142. So 1.282 plus 0.313 multiplying 3.142 or 3.14, we are getting 2.265 plus the expression. I have I here, I have I here, so that's the imaginary part. So I'm going to get 0.313 minus 1.282, but this is in pi radians, so I'll multiply the value of pi. So this is what I'm doing. I'll have I out, open bracket, 0.313 by 3.142 minus 1.282, like this. So this is what I'm doing. So this place will be negative since I have, so let me make here positive, and I clean the negative there. So this is that. So let me make it positive. So once I have this, I do this simple. So 2.265 plus I, open brackets. This time this is what? 0.313 times 3.142 minus the expression 1.282. And that is giving me negative 0.2985. So let's make it 299. So I have my ln Z to be equal to 2 plus 2 2.265 minus 0.299. But at this point, the question gave us the expression. There was no ln Z, so we have to take the ln out. So Z will then be equal to E, that is exponent. to the power 2.65 minus this I. There's an I here. 0.299I. So this becomes the solution of our logarithmic complex equation. Now let's see the ninth question. And the ninth question is saying that solve the equation z to the power 4 minus 16 is equal to 0. So z to the power 4 minus 16 equals 0. So let's quickly solve this. At this point, I'm going to introduce the de Moivre's theorem to solve this problem. So you know that z to the power 4 equals 16. I'm going to have z is equal to 16 to the power 1 out of 4. But z here is a complex number. For that reason, I'm going to convert 16 to the polar form so that I can apply the de Moivre's theorem. So this place is 4. So 16 to the polar form, you know that it's a pure real number, right? So 16 is going to give me 16 e to the power, the angle will be 0, so I have 2 pi k I. So I have z is equal to 16 to the power 2 pi, so 16 multiplying e to the power 2 pi ik, all to the power 1 out of 4. So at this point, I'll have z to be equal to 16 to the power 1 out of 4 multiplying e to the power, this will multiply everything here, so 2 pi ik all over 4. So 16 to the power 1 out of 4 is simply what, 2, right? And I'll have e to the power pi ik on 2. So at this point, to get all the values, once you have z to the power 4 equals 16, I'm expecting 4 solutions. So I'll have z1, z2, z3, then finally z4 for the values of k equal to 0, 1, 2, and 3. So this is what I'm going to do. I'll put in when k is equal to 0. That's going to give me my first factor or my first solution for the equation. So when k is equal to 0, this whole expression becomes 1. And I'll have my z1 to be equal to 2. When k is 1, I'm going to have this place to be 2 multiplying the expression e to the power pi on 2i, which is also the same as 2 open brackets cosine of the expression pi on 2 plus I open brackets sine of the expression pi on 2. And that's the second root of the equation. Then our z3, that's z2. Our z3 is simply when k is equal to 2. And that is going to give me 2 multiplying e to the power pi I. So that is going to be 2 open brackets cosine of the expression pi plus I sine pi. Sorry for I sine pi. That is the third. Then the final root is going to be when k is equal to 3. So when k is equal to 3, I'll have 3 multiplying this expression, that is 2 open brackets e to the power 3 pi on 2i right? So this is the end for the ninth question, and we found all the four roots of the equation. So let's solve the final question, which is the question 10, which is a problem involving the complex operator. So for problem 10, I'm having 1 to the power 30 over the complex operator I plus I to the power 500. All the expression to the power 1000, right? So these are huge powers, but with the application of complex numbers, we can simply do this breakdown. So 1 to the power 30, you know that is the same as what? 1, right? So I'll have 1 over I. But what is I to the power 500? So I'll take, let's say, 4. I to the power 4. 500 divided by 4, what am I getting? So that is 125. So I'll get plus I to the power 4 all to the power 125. Then to the power 1000. 1 over I is the same as negative I. Then I to the power 4 is 1. 1 to the power 125 is also what? 1. Right? Close brackets. We are getting 1000. So at this point, we are having a complex number to the power 1000. We apply the De Moivre's theorem. So our R is simply what? Square root of 2. I'm cutting things short here. Then I open brackets. Angle is tan inverse of negative 1 on 1. So negative 1. That is negative pi on 4. So negative pi on 4. So I get negative pi on 4 multiplying. Sorry, let's say negative pi on 4. This one we can't use the standard argument because it's 1000. That is a huge number. So all these expressions to the power 1000. And this will give me square root of 2 to the power 1000. Then the De Moivre's theorem will allow us to have I open brackets pi on 4. That is negative pi on 4 multiplying 1000. And realize that 4 will go into itself 1. Goes here 250. So root 2 to the power 1000, that is half of this. So 2 to the power 500, e to the power 250.